When dealing with parallel conductors in electrical systems, the National Electrical Code, or NEC, provides specific guidelines to ensure safety and proper operation. This discussion focuses on applying NEC regulations to a scenario involving a 480 volts motor control center, or MCC, with a 1200 amps incoming circuit breaker and the desire to connect a 60 amps three-phase circuit breaker in parallel to maintain control power in case the main breaker trips. The key NEC articles governing this situation are 310.15 Bone and 310.15 B2. NEC Article 310.15 Bone addresses the ampacity requirements for parallel conductors. It states that the ampacity of each conductor in a parallel set shall not be less than 1/3 of the total ampacity of the parallel conductors. This rule aims to prevent overloading individual conductors and ensures that the current is distributed safely across the parallel paths. NEC Article 310.15 B2 further clarifies the ampacity requirements for parallel conductors. It stipulates that no conductor shall have an ampacity less than that of the connected load. However, there is an exception if the conductor is protected by a fuse or a circuit breaker rated at not more than the ampacity of the conductor. This provision allows for smaller conductors to be used in parallel configurations, provided they are adequately protected against overcurrent. Now, let's apply these NEC regulations to the specific case of the 480 volts MCC with a 1200 amps incoming circuit breaker and a parallel 60 amp circuit breaker. Firstly, we need to determine the minimum ampacity required for the cable connecting the 60 amp circuit breaker based on NEC Article 310.15 Bone. According to this article, the ampacity of each conductor shall not be less than 1/3 of the total ampacity of the parallel conductors. In this case, the total ampacity of the parallel conductors is 1200 amps. Therefore, the minimum ampacity for the cable to the 60 amp circuit breaker is 1/3 of 1200 amps, which equals 400 amps. Secondly, we must also consider NEC Article 310.15 B2. This article states that no conductor shall have an ampacity less than that of the connected load. In this case, the connected load is the 60 amp circuit breaker. Therefore, the cable to the 60 amp circuit breaker must have an ampacity of at least 60 amps. Considering both NEC articles, we need to choose a cable size that meets both requirements. The cable must have an ampacity of at least 400 amps, as per NEC Article 310.15 Bone, and at least 60 amps, as per NEC Article 310.15 B2. Therefore, the minimum cable size to the parallel 60 amp circuit breaker must be rated for at least 400 amps. It is important to note that the NEC does not provide specific guidance on the maximum cable size for parallel conductors. However, it is generally recommended to use the minimum cable size that meets the ampacity requirements. In this case, a 400 amps cable would be sufficient. Choosing the appropriate cable size is crucial for ensuring the safe and reliable operation of the electrical system. Using a cable that is too small can lead to overheating, insulation damage, and even fire hazards. Conversely, using a cable that is significantly larger than necessary can result in unnecessary cost and difficulty in installation. In addition to cable size, other factors must also be considered when connecting parallel conductors, such as conductor material, insulation type, and installation method. These factors can affect the ampacity of the conductor and must be taken into account when selecting the appropriate cable size. Conductor material, such as copper or aluminum, affects the ampacity of the cable. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. Therefore, a copper cable will have a higher ampacity than an aluminum cable of the same size. Insulation type also affects the ampacity of the cable. Different insulation materials have different temperature ratings, which determine the maximum temperature the conductor can withstand before the insulation degrades. Cables with higher temperature ratings can carry more current without overheating. Installation method also plays a role in determining the ampacity of the cable. The way the cable is installed, such as in conduit, in free air, or buried underground, affects its ability to dissipate heat. Cables installed in enclosed spaces, such as conduit, will have a lower ampacity than cables installed in free air. When selecting the appropriate cable size for parallel conductors, it is essential to consult the NEC tables and manufacturer's specifications to ensure that the cable meets all applicable requirements. These resources provide detailed information on the ampacity of different cable types and sizes under various conditions. In summary, when connecting a 60 amp circuit breaker in parallel with a 1200 amps main in a 480 volts MCC, the cable size to the parallel 60 amp circuit breaker must be at least 400 amps according to NEC Article 310.15 bone. The cable must also have an ampacity of at least 60 amps, as per NEC Article 310.15 B2. It is generally recommended to use a minimum cable size that meets these ampacity requirements, while also considering factors such as conductor material, insulation type, and installation method. Consulting the NEC tables and manufacturer's specifications is crucial for ensuring compliance and safety. In addition to the specific NEC articles mentioned, it is also important to consider other relevant sections of the code when designing and installing parallel conductor systems. These may include requirements for conductor identification, termination, and overcurrent protection. Conductor identification is essential for ensuring that the correct conductors are connected to the appropriate terminals. The NEC requires that all conductors be clearly identified by color coding, marking tape, or other approved means. This helps prevent accidental miswiring, which can lead to equipment damage or personal injury. Termination requirements are also important to consider when connecting parallel conductors. The NEC specifies the types of terminals and connectors that are permitted for use with different conductor sizes and materials. Proper termination techniques are essential for ensuring a reliable and safe connection. Overcurrent protection is a critical aspect of any electrical system, and parallel conductor systems are no exception. The NEC requires that all conductors be protected against overcurrent by fuses or circuit breakers. The size and type of overcurrent protection device must be selected to protect the conductors from overheating and potential damage. It is also important to consider the coordination of overcurrent protection devices in parallel conductor systems. Coordination ensures that the overcurrent protection device closest to the fault will trip first, minimizing the impact on the rest of the system. Proper coordination can help prevent nuisance tripping and unnecessary downtime. In addition to the NEC requirements, it is also important to follow manufacturers' recommendations and industry best practices when designing and installing parallel conductor systems. Manufacturers often provide specific guidelines for their products, which can help ensure proper installation and performance. Industry best practices can also provide valuable insights into the design and installation of parallel conductor systems. These practices are often based on years of experience and can help avoid common pitfalls. When working with electrical systems, it is always important to prioritize safety. Electrical work can be dangerous, and it is essential to take precautions to protect yourself and others from harm. Some basic safety precautions include wearing appropriate personal protective equipment such as gloves and safety glasses, to energizing circuits before working on them, and using insulated tools. It is also important to be aware of the potential hazards associated with electrical work, such as electric shock, arc flash, and electrocution. Understanding these hazards and taking steps to mitigate them can help prevent accidents and injuries. In conclusion, connecting parallel conductors in electrical systems requires careful consideration of NEC regulations, manufacturers' recommendations, and industry best practices. By following these guidelines and prioritizing safety, it is possible to design and install parallel conductor systems that are safe, reliable, and code-compliant. The key considerations include selecting the appropriate cable size, ensuring proper conductor identification and termination, and providing adequate overcurrent protection. Consulting with a qualified electrical engineer or contractor is recommended when designing and installing complex electrical systems such as those involving parallel conductors. Their expertise can help ensure that the system meets all applicable requirements and operates safely and efficiently.